Hi everyone and welcome back to Null Zero Labs. On this episode I'm going to do something a little bit different. I want to try and cover OSPF. I'm going to try and break it down into like 5 videos so that we can go through everything from the very basics to expanding out into multiple areas and the different types of use cases for OSPF and how you would configure it. With a little bit of the theory side thrown in as well with a couple of slideshows. We'll see how that goes. I'm not the best person to give a presentation with a PowerPoint slide deck. I get very nervous doing it for some reason. I don't know why. So I don't know if it will come across well, but there are plenty of resources online for looking up OSPF for the in-depth technical terms of the terminology of how the link state advertisements work or tuning of the algorithm, so to speak. We're going to cover the essentials that you would need to create areas, advertise each of those areas into another area, how you accept an external redistribute external routes into your area, etc. So we're gonna build that process along. So it's going to be slightly different, a slightly different concept, but we'll see how it goes. But let's jump into the slideshow, which we'll get through. Hopefully it's only like 10 slides. You should be okay. And then we'll then jump into the configuration lab. So let's get going. Hello and welcome everyone to the slideshow part of the video. In today's video, we're going to go through some OSPF fundamentals and some basic configurations. So we're going to start with a little bit of theory and go through why it is such a crucial routing protocol to understand in enterprise and ISP networks. So let's jump. So OSPF is a link state protocol. What does that mean? It means it uses the shortest path algorithm to find its route through the network to get you to your destination. Unlike older based protocols like RIP, which are vector based, and they only know about the next hop. So OSPF is mainly used, more widely used, I should say, because of its fast convergence. It has the ability to organize areas of your network into smaller areas or multiple areas. And that by doing so, you can reduce the network overhead and increase performance, which allows you to converge faster. So the big difference in the difference between link state and vector-based routing protocols, and the main difference is that link state protocols have an entire view of the network topology within their table, and this allows them to make quicker decisions and to scale better. Whereas, like we've discussed, the distance-based protocols will only ever know about the next hop to the destination. So we have a few terminology essentials. The router ID is an ID that we use to identify the router. We normally use the loopback IP address for this. There is the DR and the BDR, the designated router and the backup designated router. They are used on multi-access networks like Ethernet, like if you had 2 routers on a switch, and it's how they go through their election process. So OSPF uses a neighbor relationship. They will start sending hellos to each other, and once they agree on the settings and the parameters that are configured on both sides, they will then form a neighbor relationship, and they will then share their routing information with each other and start to build a topology view of the network. So OSPF uses 5 different types of packets when it's going through its process of forming a neighbor relationship, and when it's sending and receiving and sharing database information. We will take a look at these later on in a Wireshark capture, and we'll be able to see these packets on the Wireshark, and they're useful for when you need to troubleshoot any issues. So these packets, these LSAs, they are sent out by all the routers that are operating within the OSPF area, so that they can then see each other and share database information between all of the routers so that everyone stays up to date. So in summary, OSPF is a 5-step process of discovery before they calculate and install a routing table. So this wraps up our boring side of the slideshow, and we're gonna jump into some configuration in the lab with a simple topology, and we're going to go through a few of the basic concepts, and hopefully I'll explain that better than doing a slideshow. So welcome to the lab. So in the lab here now we have 3 routers, and they are within, I've put this line circle around it to show that they're within a single area. So we're a single area OSPF setup is what we're going to achieve today. We're going to start by configuring our IP addressing on our network interfaces. We're going to configure some loopback IP addresses on each of the 3 routers, which we are going to use for our router IDs, as I showed in the slideshow presentation. And then we are then going to configure an OSPF process on each of these, configure them for areas, and we're going to advertise networks into the process. I'm going to do it in 2 ways. I'm going to do it using the network statements underneath the OSPF section of the configuration, and I'm also going to do it where you would see it in another way, where we advertise based on at the interface level. So we can put the commands to advertise a network at the interface level, or we can do it all under the OSPF process section of the configuration. So there's 2 ways of doing it. The way to do it under the interface can sometimes help if you're not a wildcard mask master, or you don't want to go and look up what the wildcard masks are. You can easily advertise them in by doing it at the interface level. So we'll do both ways, and so hopefully that should cover the different types of configuration style you might see on a router. So let's start on router 2 in the middle, and we're going to configure these links, these point-to-point links towards router 1 and router 3. So let's jump on to router 2, and let's start with our loopback address, which is this one here. So we're going to go int L0. This will create a loopback interface for us. We see there it goes. And we're going to go description. This is R2 loopback. And the IP address is going to be 2.2.2.2, 255.255.255.255. So that's basically a single address, a /32. We don't need to use a no shut because a loopback interface is always up. So next, let's do E0/0. We're going to give it a description, and this is link to R1. It's going to have an IP address of 10.1.1. Let's go with a 1, 255.255.255.252. That means it's a 2 IP addresses, a /30 point-to-point, and we'll no shut that interface as it's a Ethernet interface. And then we will jump over to int E0/1. Description is going to be link to R3, sorry. And the IP address is 10.1.1. We will use 5. And we will no shut that. So let's save that. So we've configured the IP address of this interface, and the loopback. So now let's jump to router 1, and we will do the same for its interfaces. So again, enable mode, configuration mode. in L0, and its IP address is going to be 1.1.1.1, 255.255.255.255. Description, this is going to be R1's loopback. And now int E0/0, the IP address is going to be 10.1.1.2, 252. And the description is going to be link to R2. We no shut that. Int E0/1, the IP address is going to be 192.168.1. Let's do 1.1. And that's a /24. Oh. IP address. There we go. And we will do a description, and this will be R1 LAN. And we will do a no shut. So this interface configured, our loopback configured. This link now has an IP address on this side of the link, this side of the link. This has an IP address, this has an IP address. Now let's jump to R3 and configure its interface towards R2, its LAN interface, and its loopback. So onto R3. Let's start with our loopback address, int L0, and this will be R3's loopback. We give it an IP address of 3.3.3.3. These addresses are obviously so you can visually see the different routers. Int E0/0, which is the int E0/0 description. This is going to be a link to R2. Its IP address is going to be 10.1.1.6. No shut. And int E0/1 description. This will be R3 LAN. And it's going to have an IP address of 192.168.2.1 and a /24. No shut. Okay, so we've configured our interfaces. So every interface has got an IP address. But now if we go from R3 and we say we want to ping 192.168.1.1 with a source of E0/1, we can't get there. And we all know why we can't get those, because none of these routers have a routing table. So if we show IP route, well, let me reframe that. They do have a routing table for their directly connected information. So router 3 knows about its loopback, it knows about its LAN address, and it knows about this interface towards R2. And it'll be a similar story on all of them. What we need to do now is make these routers advertise their networks to every other one, so that this router knows about this leg, knows about this network, knows about these loopback addresses, and likewise so that router 1 knows about this leg, these loopbacks, this loopback. And so we want every router to have a picture of what this network looks like, so that traffic can flow from desktop 4 to desktop 5. So let's start with R1. We'll start on the left, and we will do this we'll do this configuration under the OSPF process. So this one I'm going to use the network statements to advertise the networks into OSPF, rather than using the interface style of commands. So let's start on R1, so config T, and I'm going to start with a router OSPF, and then we need to give it a process name ID. So this is a local process ID because you can be running multiple OSPF processes. So we're going to use 2025 for the year. So that's our OSPF process. The process number doesn't have to match on each router, just so that you know this is just a process ID that's local to the actual router. So now we're going to set our router ID, and our router ID should be our loopback address, which we've already configured, 1.1.1. Now, I'm going to use a command here that you should always use, which is passive interface default. And what this is going to do is it's going to put all interfaces for OSPF into a passive state. Now, earlier in the slideshow, we said about how routers create relationships. They create the relationship by sending hello packets. Now, sending hello packets and creating a relationship is one thing. Advertising the network is another. So on this leg here, we've got no other router. We don't want to advertise or start another OSPF adjacency with anything on this side of the network. We just want to advertise this network. So we don't want to run the risk of somebody plugging a router in and it joining our OSPF process and causing hell with our network. So we're going to say, hey, every interface by default is a passive interface unless we say otherwise. So we don't need to worry about our loopback, and we don't need to worry about this one, but this one we do want to form a neighbor relationship with R2. So I'm going to say no passive on this one. So no passive interface is going to be E0/0. So what we've done is we've said, hey, on this interface, I do want you to not only advertise, but I also want you to create a neighbor relationship with another router. Okay, so now that we've done that, let's advertise our network. So we're going to start by advertising our loopback. So we're going to use the network command, and our first one is 1.1.1.1. And now this is a wildcard mask. So let's bring up a wildcard mask calculator. So here I have my calculator, and I'm going to generate a wildcard mask for this address. So 1.1.1.1, and we know it's a /32. So the subnet mask, as we know, is 255.255.255.255, which we know. Now, I'm not a mathematician, and we do have modern technology these days, so you can use there's no reason not to use a subnet calculator. So if I tick this box, we'll see that the wildcard mask is all zeros. So we're saying we want to match, 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 match. Anything that has like a 255 or a different number based on the subnet is what we can be anything. So if we take this /30 subnet, for example, which is 10.1.1.0/30, we can see that the wildcard mask is 3. So we want to match, match, match all of these. And then this last bit, we're saying it can be either the 1 or the 2, basically the 2 hosts that are available. So that's how we match. So that's what that means. Our /24 is going to be 0.00255, which is an easy one. That's why I added this one here. I could have done them all as /255 for /24, but you wouldn't have seen that there is a difference between the wildcard masks. And this is the thing when you do it with this standard of doing it under here. When I do it in the next one, you'll see that you don't have to. So then we know that the wildcard mask for this is 0.0.0. Next, we're going to say, because we're only doing a single area, and this is our beginning area, it's in area 0 or the backbone. So you can either put it in as like this for area 0, or you can put it in like this. So there we go. So we're saying we're advertising this network into area 0. Now let's advertise our LAN, so network again, and it's going to be 192.168.1.0. And we know that the wildcard mask, we need to use 0.0.0.255. And again, we're going to advertise that into area 0. Now, our non-passive interface, we're going to advertise this into here. But because it's a non-passive interface, once we start the configuration on R2, we'll see that the routers will go through their hello process, and they will then start to form an adjacency, and router 2 will start to learn about all of the networks from router 1. So when we start configuring this, I'll do a capture on router 1 as well, and we'll be able to see hopefully that process happen. So finally, let's advertise our final network, which is 10.1.1.0, and it's a /30, so it's 0.0.0.3, and we're advertising that as well into area 0. So we're doing just single area. Now, we're not obviously going to go into any tuning or anything like that, but we will do at a later date where we will specify that these are a point-to-point, because it speeds up the OSPF process, because we know that there's never going to be any other routers on this network, so we can speed that up. We could actually do that. Actually, we will do it by default. So we'll go into int e0/0. And this is where you'll find that you end up putting some commands under the network interface, some commands under the actual OSPF process. So let's do that now, and we're going to do it by typing IP OSPF network, and we're going to say that this is a point-to-point. Now I'm going to write that out. So we've now configured OSPF on router 1. Now let's jump to router 2 and configure router 2. So here we are on router 2. So again, we're going to configure OSPF, but this time what I'm going to do is I'm going to configure the commands on the actual interface rather than at the OSPF level. So this is the second way of doing things I'm going to do for this router. What I'm also going to do is I'm going to start a capture on the interface that's going towards router 2, so that when it comes up, we'll see the OSPF. We can already see, there we go. We can see OSPF is sending a hello packet out to this multicast address, the 224.0.0.5 address. So we can see it sending out its hello packets, along with, we've got CDP enabled, so we can see CDPs going across there. Let's turn that off so that we don't get that information coming across as well. So we're going to int e0/0, and we will do the no CDP enable, so that we don't get any CDP traffic on that interface as well. So we'll let that keep capturing so we can see the hello coming from the OSPF. So it's going, hello, is anybody out there? Anybody want to have a neighbor relationship? And that's what we've blocked on this side by putting these into a passive state. So back to R2, because I jumped around there. So we're going to go int, no we're not, we're going to go router, OSPF, and I'm going to 2025, I'm going to give it the same process name. The router ID is going to be 2.2.2.2, which is what we set for the loopback. And that makes it easier to, not only once you know what the loopback IP address is, when we do the diagnosis, you'll see the router ID showing so you can identify each router. Right, so now that we've done the router ID, we're going to do our passive interface, default. So, and then we're going to say no passive interface, no passive E0/0, and no passive E0/1, because we're going to form a neighbor relationship with E3. So those are our two that we do not want to have a so we look at the configuration so far. So there we go. We can see that we've created the OSPF process, we've given it its ID, and then we've said put all the interfaces into a passive state, unless I then say which interfaces are allowed to run OSPF processes. So now let's advertise the networks. This time I'm not going to do it under this section. I'm going to do it under the actual interfaces, and you'll see how that's done now. So let's start with the loopback. So int L0, I'm going to go IP OSPF, and we put the process ID, which was 2025, and then we're going to set the area to 0, and that's it. So now we're advertising that interface into OSPF. So do show run int L0, and we can see IP OSPF, this process, advertise it into area 0. So much easier than having to remember what a wildcard mask is. So now let's do int E0/1, the one towards router 3, IP OSPF 2025 as the process, advertise it into area 0, and run the process there because we've set it as a non-passive interface. Now let's do this one towards router 1, and what we should see is our Wireshark should start to see a whole bunch of traffic, a whole bunch of packets, I should say, transverse backwards and forwards as the two routers negotiate and form an adjacency. So let's go into int E0/0. And what we will do is, first of all, I'm going to turn off CDP so we don't see that traffic on our Wireshark. So no CDP enable. Now I'm going to do IP OSPF 2025 area 0. Now let's go and have a quick check of our Wireshark. So here there we go, found it. So there we go. We can see we've got they're starting their process of communicating with one another. With one another, we see the request. See, there we go. We can see the LSA coming from this router ID, advertising this router ID. They're then doing an update of a type 1 LSID. We can then see, there we go. We can see that they're advertising their networks. We can then see the acknowledgement requests. So we can see the communication happening between the two devices. We can also see on the routers that there was, there we go, there is a potential mismatch. So there we go. So if we look, what's the problem? The problem is, if I do a show run int E0/0, is that I have failed to say that this is a point-to-point interface. So that can cause a problem, so we will fix that. So we'll go into int E0/0, and we'll do IP OSPF network is a point-to-point link. Now that I've changed that, you'll see that the OSPF process will start again because the interface changed. You'll see that they'll go through the whole process of agreeing again and sharing their databases with each other. So we can see this router and this router are attached. We then get the acknowledgement, which is the last part. So we've got the hellos. We then got them sending the database information backwards and forwards. We've then got them updating, and we've then got them acknowledging that they agree, and then they then start their adjacency. So now if we jump over to router 1 and we do a show IP OSPF neighbor, we can see that router 1 has a neighbor relationship with router 2. If we go to router 2, show IP OSPF neighbor, we can see that router 2 has a relationship with router 1, neighbor 11111, and the state is full. So now if we do a show IP route on router 1, we can see that it has an OSPF record, another OSPF record, so 2. because it already knows about this network. It already has this. It doesn't need to have this network advertised to itself from this side. So it already knows about that one. So it's now learning about this subnet and this subnet. So now router 1 knows this subnet and it knows how to get here. So if we do a show IP route OSPF, we can see the two routes that we learned from router 2. Likewise, if we go on to router 1 and we do a show IP route, and I'll do it as an OSPF, we can see the two routes that were learnt from router 1, which was the /32 and the LAN subnet. So now let's configure router 3. And what I'll do before I do that is, because again, this is a point-to-point, int e0/1, we'll do IP OSPF network point-to-point. We've got our OSPF configuration underneath our interfaces, and we have our OSPF process where we have set our router ID and our non-passive interfaces. If we look at router 1, we can see we have no OSPF configuration apart from that it's a point-to-point on this link. And we are advertising doing all of our advertising of our network under the actual OSPF process. So let's jump to router 3 and we'll do a similar configuration. Again, I'm going to do this under the interface because that's my personal preference for configuring OSPF. I like to leave the all of the configuration information for advertising the networks into OSPF via the interface rather than doing it under the OSPF process. Again, also because I'm lazy and I don't like having to go and check wildcard masks. So let's start again with IP. We're going to do router OSPF and the process is going to be 2025. The router ID is going to be 3.3.3.3. And our passive interface is going to be default. So all interfaces are passive. And we're going to do a no passive interface on E0/0. What we will do as well is we'll do a capture on E0/1 later so that we can see the difference between a passive and a non-passive. So E0/0, no passive. So that's all we need to do under the OSPF section. I'm going to go into int L0, IP OSPF 2025 area 0, in E0/0, IP OSPF network is going to be point-to-point, and IP OSPF 2025 area 0. We're going to advertise that, and then int E0/1, IP OSPF 2025 area 0. I'm going to write that. So that is our configuration, just like that. Boom, it's that quick. So now if we have a look at Wireshark again, we can see some more updates coming through. So we've had another acknowledgement. Router 3 is sending out information into area 0. So router 1 has learned about it. Router 2 has acknowledged it. And now we can see the continual hello packets, which are used to make sure that links are up. And that's how they determine whether or not a change needs to happen. Now, if we jump over back to router 1, we do a show IP route OSPF. We can see that we now have more entries. So we've now learned about the .2 network over here. We've learned about the 10.1.1.4 network, which is this one here. We can see that we've learned about the /3 which is this loopback address here. And we can see that we've learned about the /2 address here. Obviously, router 1 knows about this one, knows about this one, knows about this one, because they're directly attached. So for traffic to get from here to here, we've had to learn about this middle hop and this network, and we've had to learn about this hop and this network. So now, if I go over to router 3 and we do a show IP OSPF neighbor, again, we can see that we've got a neighbor relationship with router 2. If we add another link going between these router 1 and router 3, you'll see that router 3 will have a neighbor relationship with router 2 and with router 1. But as it stands, we are in a straight line. We have a neighbor relationship with this one. Router 2 has a neighbor relationship with both of us. So if we do a show IP OSPF neighbor on router 2, you can see that router 2 knows about router 1 and it knows about router 3. So now that we've verified that we've got OSPF running and we have an OSPF relationship between each of our routers and we have a routing table on each device, now let's do a verification of the path. So let's do a ping. Let's ping the loopback of the other end 3.3.3 with the source of 1.1.1.1. And there we go. We can see our loopback can ping the loopback there. And we should be able to ping 2.2.2.2. Yes, we can. And we should be able to ping our desktop if it's on 192.168.2.10. There we go. We can reach our desktops. Now let's do one final test and we'll test that we can get full connectivity from desktop 4 to desktop 5 and make sure that we've got our full path. So let's open our terminal and we'll ping 192.168.2.10. And there we go. We can see we have data flowing from desktop 4 all the way through our OSPF configured network to desktop 5. So that's it. The basics of OSPF in a single area. In our next video, we're going to look at OSPF on a multi-access network medium, like multiple routers connected to a switch. In this video, we've learned that OSPF is a link state protocol. It is an open standard. It is an interior gateway protocol. We've learned that it uses LSAs to communicate and form adjacencies between each of its participating neighbors. We've learned about the wildcard masks. We've also learned about the router IDs, the concept of a passive and a non-passive interface. We've learned, what else? We've learned the two different ways of configuring OSPF based upon doing it under the actual OSPF process or by doing it at the actual interface level. Next week, we will move on to expanding upon this, and we will show what happens when you have multiple routers, not just in a point-to-point configuration like this, but on a multi-access medium. So we have multiple routers connected to a switch and how they will go through their election process for who is the designated OSPF router and who is the backup designated OSPF router. So look forward to that video. Get liking and subscribing, and I'll see you for that one. On another note, I've got some hardware winging its way to me, which is a few Metro Ethernet switches, where we're gonna wire them up, and I'm going to show you how you can put a loop in an Ethernet switch network and do it safely when you're creating a Metro Ethernet LAN, which is useful in metropolitan areas like big cities for when we want to connect multiple buildings together at a service provider level. So I've got 3 of those Metro Ethernet switches coming. I'm going to get those configured and then I'll pop a video up about that as well. So I'll see you on the next one for the next OSPF one. That may take a little while because having to do slideshows takes a little bit of time to put together and I'm not the best at it. But in the meantime, there'll be that. Switching one to look out for. There may be one that I'm going to do about what we call a poor man's MPLS, where we can do a layer 2 over the internet for you, because I realized I did that in my blog, but I didn't do it as an actual video. So I've got 2 other concept videos that I want to get put together for you guys, and part 2 of the OSPF series. It'll be a 5-part series in total, so this is one of 5. So other than that, have a good weekend, and I will see you next time.